at the western edge of the Pacific Ocean, where the seafloor has been pulling apart and pressing together for longer than most of the land on Earth has existed. One vast plate of stone bends downward beneath another. The motion is imperceptible. It proceeds at roughly the pace a fingernail grows, 2 to 3 centimeters each year, and yet over tens of millions of years, that unhurried descent has opened the deepest wound in the ocean floor anywhere on the planet. The stone does not fall. It tilts. It inclines. It angles downward at perhaps 45 degrees, sometimes steeper, and follows a path into the interior of the earth that it has been following since before the first flowering plants appeared on land. The place this motion has made is the Mariana Trench. It runs in a long, gently curving arc through the western Pacific, stretching for roughly 2,500 kilometers longer than the continental United States from coast to coast, though narrower, averaging only about 40 miles across. Its walls fall away from the surrounding seafloor at angles as steep as a mountain face. The water above it is some of the deepest in any ocean, and at its southern end, tucked into a depression that represents the absolute terminus of the Pacific Plate's long descent, lies the deepest confirmed point on the surface of the Earth. That point is called Challenger Deep. It sits roughly 300 kilometers southwest of the island of Guam, an unremarkable stretch of open blue water at the surface, indistinguishable from the thousands of kilometers of Pacific surrounding it. Beneath that surface, the seafloor drops away for nearly 7 miles. The number is precise and confirmed, approximately 10,935 meters, a figure arrived at through sound rather than sight, through the careful measurement of how long it takes a pulse of sonar to travel to the bottom and return. It is a depth that has no easy comparison in the world above water. If the tallest mountain on land were placed inside it, the mountain's peak would still be submerged by more than a mile of ocean. The trench's arc shape is not accidental. It is the direct expression of the geometry of subduction, the process by which one plate of oceanic crust slides beneath another along a convergent boundary. Where two plates meet and one is forced down, the descending plate bends along a curved line determined by the spherical surface of the Earth. The result, visible from above in the topography of the seafloor, is a long bow of deepening water, concave on the side from which the descending plate arrives, convex on the other. The Mariana Trench bends in precisely this way. Its arc is the signature of the Pacific Plate's edge, pressed into the stone of the seafloor over time, so deep and so long that the impression has become permanent, or as permanent as anything made of moving rock can be. The Pacific Plate itself is among the oldest oceanic crust on Earth. The rock now arriving at the Mariana subduction zone solidified from cooling magma during what geologists call the early Jurassic period, a time when dinosaurs had only recently begun to diversify on the land masses of a world that looked nothing like the one above the water today. That was roughly 180 million years ago. Since then, the crust has traveled slowly westward and southward across the Pacific Basin, moving in the imperceptible way that all oceanic crust moves, carried by the convecting currents of the mantle beneath it, spreading away from mid-ocean ridges, cooling and thickening and growing denser with every million years that passes. Density is the reason this particular plate descends as steeply as it does, and why the trench it creates reaches the depths it reaches. Old oceanic crust is cold oceanic crust. Cold crust is dense crust. And dense crust, when it meets another plate at a convergent boundary, sinks rather than floating, pulled downward by its own weight into the mantle below. The Pacific Plate, being exceptionally old and therefore exceptionally cold and dense, sinks at a particularly steep angle. It does not ease gently into the mantle at a shallow slope. It tilts and descends at angles approaching 45 to 60 degrees. And the steeper the descent, the deeper the trench above it, because the bending of the plate at the surface must accommodate the sharp angle of its plunge below. At the surface of this process, and surface is a relative term at such depths, the trench floor is not a single flat plane. Challenger Deep is divided internally into 3 distinct basins, arranged in sequence along the trench's length like a chain of submerged valleys. They are called the Eastern Pool, the Central Pool, and the Western Pool, and each is separated from the next by a low ridge of deformed rock and compacted sediment that rises from the otherwise flat bottom, a saddle of compressed material crossing the trench floor between one deep basin and the next. The deepest of these basins, where the greatest confirmed depth has been measured, lies in the Eastern Pool. The others are marginally shallower, but all 3 rest at depths that no sunlight has ever touched, in water that has been cold and dark, and still for longer than there have been humans to wonder about it. The walls of the trench rising from those basins toward the surrounding abyssal plain are among the most dramatic geological features on the ocean floor. The surrounding seafloor itself sits at depths of 5,000 to 6,000 meters, already well below the reach of any light, already cold and pressurized beyond anything experienced at the surface. From those depths, the trench walls descend for another 5,000 meters or more, plunging at angles that in places rival the face of a steep mountain. The rock that makes up those walls is a mixture of old oceanic basalt, sediment compressed into stone by the weight of the water above and the pressure of the surrounding geology, and material deformed by the immense forces operating at the contact zone between the 2 plates. It is not smooth. The walls are fractured and faulted, broken into terraces and overhangs by the continuous grinding and flexing of the subduction process. The trench is not a clean valley, it is a wound in the seafloor, and like all wounds, its edges are complicated. The descent of the Pacific Plate into the mantle does not happen quietly in the geological sense. The contact between the 2 plates, the megathrust fault that defines the subduction zone, is one of the most seismically active regions on the planet. Where the plates lock and then release, earthquakes radiate outward through the crust and the ocean. The Mariana region has a long seismic history, its rocks continuously deformed by the forces of convergence. The plate that is descending carries the chemical record of its long ocean crossing. Hydrated minerals formed as seawater infiltrated the crust through cracks and fractures over millions of years. As that crust descends into the mantle and heats, those water-bearing minerals release their fluids. The fluids rise through the overlying plate. They alter the melting point of the rock above. And in the Mariana Arc, the chain of volcanic islands and seamounts that runs parallel to the trench on the landward side, they feed the volcanoes that have been building above this subduction zone for tens of millions of years. The arc itself is a secondary expression of the same fundamental process that made the trench, where the subducting Pacific Plate releases its fluids into the mantle wedge above. The rock there melts at lower temperatures than it otherwise would. That melt rises through the overlying crust. Some of it erupts at the seafloor. Over time, the eruptions build volcanic structures, seamounts, some of which have grown tall enough to breach the surface as islands. The Mariana Islands themselves, from Guam in the south to the northern volcanic peaks, are the surfaced summits of this arc, standing above the water while their foundations stretch downward into a seafloor shaped by the same plate collision that lies 40 miles to the east. Within this arc, at sites where the volcanic and hydrothermal activity reaches the seafloor, the ocean encounters conditions unlike those anywhere else in the shallow or middle ocean. Hydrothermal vents are not unusual in the deep ocean. They occur along mid-ocean ridges worldwide, wherever hot rock meets cold seawater through cracks in the crust. But in the Mariana Arc, the specific chemistry of the arc's volcanic system has produced something that has no equivalent at the mid-ocean ridges. At a site called Champagne Vent, located in the arc rather than in the trench itself, but within the broader Mariana system, the hydrothermal fluid that rises through the seafloor is not the superheated mineral-laden water that characterizes the black smokers of the mid-ocean ridge. Instead, it is liquid carbon dioxide. Carbon dioxide, the same compound that dissolves in water to create the carbonic acid found in rain, the same compound that exists as a gas at every temperature and pressure, familiar to life at the surface, behaves differently under certain combinations of deep sea pressure and temperature. At depth, under the right conditions, it can exist not as a gas, not dissolved in the surrounding water, but as a liquid with a density close to that of seawater, separate from it, pooling and flowing in a way that gas cannot. At Champagne Vent, streams of this liquid carbon dioxide rise from cracks in the seafloor in pale, wavering columns. They are not the dark mineral-laden plumes of black smokers. They are nearly clear, a slight shimmer in the water, a visual distortion where the liquid CO2 and the surrounding seawater meet at the boundary between their different densities. The columns rise slowly, catching and refracting the light of any instrument trained on them, then pooling briefly in shallow depressions in the volcanic rock before gradually dissolving into the surrounding cold water. The process has no surface equivalent. It is a feature of a specific depth, a specific temperature, a specific geochemistry, conditions that exist in this form in almost no other place on the ocean floor. The name Champagne Vent comes from the appearance of the rising fluid, the small bubbles and larger wavering masses of liquid and dissolved gas, giving the site a visual resemblance, from the right angle and with the right light, to something effervescent, something rising through a glass in a bright room. It is a small domestic image for something so remote and so geochemically strange, but it is accurate in the limited way that surface comparisons can be accurate for things that exist only in the dark and the deep. The vent releases its liquid carbon dioxide continuously, steadily, with the same unhurried persistence that defines every geological process in the Mariana region, a slow emission from the interior of the Earth, conducted without interruption in the cold and the dark, at the edge of a subduction zone that has been operating since long before the first human eyes opened anywhere on the surface of this planet. The surrounding water accepts the released carbon dioxide in the way that the deep ocean accepts most things, gradually, through dissolution, through pressure, through chemistry. Carbon dioxide dissolved in seawater produces carbonic acid. Carbonic acid shifts the pH of the surrounding water downward toward acidity. In this way, the chemistry of the hydrothermal fluid released at Champagne Vent moves outward into the water column around it, altering the local geochemistry in a plume that extends away from the vent site in whatever direction the slow bottom currents carry it. The effect dissipates with distance, diluted by the vastness of the surrounding water. But near the vent itself, the chemistry is distinct, a local condition shaped by the meeting of volcanic heat and cold oceanic water, a small zone where the rules are different from the open ocean around it. To understand why this matters, it is worth sitting with the scale of the geological forces that produced it. The Pacific Plate has been crossing the Pacific Basin for roughly 180 million years. It has moved during that time by a distance measured in thousands of kilometers, a slow drift barely faster than the growth of a human fingernail, compounded across geological time into continental displacement. The crust that is now sliding beneath the Mariana Plate formed at a spreading ridge, cooled, traveled, and has arrived at this subduction zone, having carried the chemical signature of its long oceanic crossing in its structure. The water that infiltrated its cracks when it was young, the sediment that accumulated on its surface over millions of years, the minerals that crystallized in its pores and fissures, all of these are now being carried downward into the mantle, or released into the overlying crust, or erupted in the arc volcanoes, or emitted at vent sites like Champagne Vent, as the plate completes what was always the final stage of its journey. The trench that is formed at the front of this subduction is, in this sense, a record of a process. Every meter of its depth corresponds to rock that descended, to crust that was consumed, to geological time that passed. The depth of Challenger Deep is not simply a measurement of water. It is the accumulated expression of tens of millions of years of convergence, of old, cold, dense crust descending into the mantle, of the seafloor bending and fracturing and yielding to forces too slow to observe, but too large to resist. The three basins of Challenger Deep, separated by their low saddle ridges, reflect local variations in the rate and geometry of that descent. Places where the bending plate dipped a little deeper, where the fault geometry allowed a little more subsidence, where the sediment filling the trench floor was a little thinner and the rock a little lower. In the surrounding abyssal plains, at depths of 5,000 to 6,000 meters, the seafloor is relatively flat, covered in a slow accumulation of sediment, the remains of creatures that lived and died in the water column above, the dust of continents carried out to sea by wind and river, the fine particles of volcanic ash from eruptions on the Arc and elsewhere. This sediment accumulates at rates measured in millimeters per thousand years. It is one of the slowest processes of accumulation anywhere on Earth, and yet even at those rates, over the tens of millions of years, the abyssal plains have been receiving it. The layer of sediment on the surrounding seafloor has built up to thicknesses of hundreds of meters in places. The trench itself being a topographic low point into which sediment slides from the surrounding slopes, receives a somewhat different accumulation, sediment delivered not only from above, but from the trench walls, cascading down in slow flows that deposit their load on the trench floor in layers that record each such event, to stand, in imagination and the slow drift of attention, at the rim of the Mariana Trench on the seafloor, and look downward would be to face a darkness that no light reaches from above, a drop whose base is another 5 kilometers below the point of standing, walls that angle away at slopes approaching those of a steep hillside. The abyssal plain stretches flat and pale to every other horizon. The sediment under the imagination's feet is soft and cold, the color of pale clay, marked by the faint trails of organisms moving through it in patterns too slow to observe in any single visit. And before you, though before is a difficult direction, in a place where there is no sun to mark east or west, the trench opens, the walls drop away. The darkness below is not different in kind from the darkness of the surrounding abyssal floor, because there is no light anywhere here to mark the distinction. But the pressure below is different. The cold below is structured differently. The water below is older and stiller and heavier in its column than anything in the surrounding plain. The Mariana Trench is often described as remote, as extreme, as inaccessible. These words are accurate in the sense that very few human instruments and no unaided human body has ever reached its floor, but they miss something important about the nature of the place. The trench is not an anomaly in the Earth system. It is a direct and necessary product of the way the Earth works, of the convective circulation of the mantle, of the creation and destruction of oceanic crust, of the continuous recycling of surface material back into the interior that has been operating for billions of years and will continue long after the current configuration of the Pacific and the surrounding plates has been entirely reorganized by the same slow forces now operating. The trench is not extreme in the way that unusual events are extreme. It is extreme in the way that the logical outcome of persistent fundamental processes can be extreme. The deepest expression of something that is happening everywhere along subduction zones throughout the ocean, simply carried further here by the age and density of the crust involved. The Pacific plate bends downward right now, as it has been bending for tens of millions of years, at a rate that cannot be felt from the surface. The water above the subduction zone sits calm under whatever weather the Pacific sends across it. The trench below is cold and dark and still, and somewhere within the broader Mariana system, at Champagne Vent, pale columns of liquid carbon dioxide rise from the seafloor in slow wavering streams, pooling in the depressions of volcanic rock for a moment before dissolving into the water, a process as quiet and continuous as the subduction itself, as unhurried as the descent of a plate that has been traveling since the dinosaurs were young. The carbon dioxide released at those vents did not originate at the vent. It originated in the rock of the descending plate, in the organic material and carbonate minerals carried down with the subducting crust, released by heat and pressure as the plate descended, migrating upward through the overlying rock, finding a path to the seafloor, and emerging in liquid form into water, cold enough and pressurized enough to allow it to exist in that state for the brief moment before dissolution. The element has traveled a path that began millions of years ago in the chemistry of the ocean floor, passed through the interior of the earth, and returned. It rises through cold, dark water in pale columns, wavering slightly in whatever slow current moves near the vent. And then it dissolves, taken back into the chemistry of the deep ocean, carried away in solution, eventually to participate in whatever processes the ocean conducts with the carbon it holds. There is something in this that gestures at the patience of geological process, not a patience that is chosen or felt, because the rock and the water and the carbon have no feeling, but a patience that is simply the nature of processes operating at scales of time and force that make the entire span of human history, from the first fires to the present moment, into something that would not register as a pause in the longer record. The Pacific plate has been moving toward this subduction zone since before the first dinosaurs. It will continue to be consumed here, or its successor will, long after whatever comes after human civilization has passed. The trench will deepen or shift or close according to the geometry of whatever plate reorganization the future Earth undertakes. The vent at Champagne may persist for centuries or be sealed by a lava flow from the arc above within a generation. None of these futures is legible in the present configuration of stone and water. What is legible is the current state, the arc of the trench, the depth of Challenger Deep, the three basins in sequence along the trench floor, the walls dropping steeply from the surrounding abyssal plain into darkness below darkness, the oldest seafloor on the planet sliding steadily downward at the rate of a growing fingernail, carrying its cargo of crystallized seawater and compacted sediment into the mantle, the volcanic arc above, building its islands from the recycled material of the descending plate, and at a specific site within that arc, the strange and particular phenomenon of liquid carbon dioxide rising from the seafloor in pale, wavering columns, pooling briefly in the rock's depressions dissolving into the surrounding cold, and disappearing, continuing, without witness, a process as old as the vent's first opening, as indifferent to observation as the motion of the plate itself, as quiet as the deepest water in the world, sitting still above it all, in the permanent and ancient dark. The trench does not require anything from the surface to continue being what it is. The plates do not need the ocean above them to maintain their motion. The vent does not need to be seen to release its carbon dioxide. The subduction zone operated for tens of millions of years before any creature with the sensory apparatus to notice it evolved, and will continue after the particular arrangement of life, now present on this planet, has been replaced by whatever comes next in the long biological history of a living world. In this sense, the Mariana Trench is entirely indifferent, not hostile, not alien, simply complete in itself, a feature of the Earth's surface and interior that exists according to its own conditions, governed by pressure and temperature and the composition of the rock, tended by geological forces that have no awareness of tending anything. To think about the trench at this scale, the scale of plates and millions of years, and the chemistry of the Earth's interior, is to feel something shift in the perception of ordinary time. The few centimeters the Pacific plate moves each year become, across 10 million years, hundreds of kilometers of ocean floor consumed. The slow accumulation of sediment on the abyssal plain becomes over tens of millions of years, a record of everything that lived in the water column above. The small continuous release of carbon dioxide from Champagne Vent becomes, over the lifetime of the vent, a contribution to the chemistry of the deep Pacific that is real and measurable and connected to the chemistry of the ocean as a whole. Scale does not change what is happening. It only reveals how much of it there is, how long it has been happening, and how deeply embedded in the structure of the planet it is. The walls of Challenger Deep rise from those three basins, eastern, central, western, toward the surrounding abyssal plains, climbing steeply through the dark water. The ridges that separate the basins from one another are low and broad, made of the same compacted sediment and deformed rock that carpets the trench floor between them. The deepest point in the eastern pool is the deepest confirmed point on Earth's surface, and the water above it is a column nearly 7 miles tall, a column of pressure, of cold, of absolute darkness, of chemistry that differs subtly from the open ocean at the surface. That column rests on the sediment of the trench floor, the way all water rests on what is below it, without agency, without preference, simply as the consequence of gravity operating on the mass of the ocean. And the plate below that sediment descends. It descends now. The same process that has been operating since the Jurassic continues in the present, at the same pace, at the same angle, in the same direction. The stone that has been traveling since the dinosaurs were diversifying on land is arriving at the trench right now, at the rate of a few centimeters per year, bending downward into the mantle. Its age and its density, the reason the trench is as deep as it is. The oldest floor of the Pacific, completing its crossing of the world's largest ocean, arriving at the place where the ocean floor ends. Somewhere in the Mariana Arc, not far from the trench in the scale of the Pacific, but in a geologically distinct setting, the Champagne Vent releases its pale columns of liquid carbon dioxide into cold seawater. The columns rise. They waver in the slight current near the sea floor. They catch, in any light that falls on them, the faint shimmer of a boundary between two fluids with different densities, the liquid CO2 and the surrounding water, each occupying its own chemistry in the same small volume of deep-sea space. The columns reach upward a short distance, pool for a moment where the rock dips into a slight depression, and then dissolve slowly, continuously, completely, into the water that surrounds them, and are gone. The vent continues, the columns form again, the water accepts them. The process neither hurries nor pauses, carried forward by the same geological forces that have been operating here since before the ocean above this place had its current form. The earth makes new conditions for itself in the dark. It has been doing so since long before any eye existed to observe it. The trench is one of those conditions, a place arrived at through the patient arithmetic of plate motion and geological time, now as much a feature of the planet as the continents and the mountains and the spreading ridges of the open ocean. What happens inside it, in the cold and the pressure and the dark, is a continuation of what happens everywhere in the Earth system, only carried further, deeper, older, more compressed, more still. And at the edge of that stillness, in the quiet of the deepest water, columns of pale liquid rise from the seafloor, pool, dissolve, and rise again. The planet turning its chemistry over in the dark, unhurried as it has always done, in the particular and ancient silence of the deep. At the floor of Challenger Deep, where the water column above measures nearly 7 miles from surface to sediment, the pressure arrives not as a sensation, but as a fact of physics, so complete it becomes invisible. 1,086 bars. That number, set plainly against the silence of the deep, asks to be felt rather than counted. A single bar is roughly the weight of the atmosphere pressing down on every square inch of the surface at sea level. The pressure a body moves through on an ordinary day without noticing, so familiar it has no texture at all. Now take that familiar weight and multiply it by more than 1,000, and let the product rest on a square meter of pale sediment at the bottom of the world. What presses there is not violent. It does not surge or strike. It simply is, in every direction at once, carried by the water itself, with the same patient evenness that water has always carried weight, transmitting force laterally, inward, upward, through every molecule of the column above, from the sunlit surface all the way down to the stone. The water does not resist this. It accepts the pressure without compression, without collapse, without any outward sign that something extraordinary is happening inside it. A sealed metal drum, lowered to that depth, would fold inward almost instantly, its walls giving way not with a dramatic implosion, but with a quiet, irreversible caving, as the pressure outside surpassed everything the metal could hold. The water surrounding it would not flinch. It would continue, as it always does, pressing equally against every surface, filling every space, transmitting the weight of 7 miles of ocean downward into the floor of the trench, as though this were the most ordinary thing in the world. And for the water it is. The pressure at Challenger Deep is simply the consequence of that much water existing above a single point, gathered there by gravity over millions of years, held in place by the shape of the crust beneath. It is not an event, it is a condition. It is the permanent weather of the deepest place on earth, and it has been this way for longer than there have been creatures capable of registering it as anything at all. The walls of the trench rise on both sides into the absolute dark. At their base, where the sediment meets the lower slopes, the floor is nearly flat, a pale, cold expanse of fine-grained material, lying undisturbed under a weight that has not changed meaningfully in eons. The pressure does not fluctuate with the seasons. It does not ease at night and tighten in the day. It is not affected by storms on the surface, by the passage of ships overhead, or by any of the rhythms that govern the upper ocean. Far below the last stirring of tidal influence, beyond the reach of any current that moves with intention, The weight at the floor of Challenger Deep simply sits constant, year after year, decade after decade, geological period after geological period, pressing on a floor that has never known anything else. The temperature at that depth holds between roughly 1 degree and 4 degrees Celsius, just above freezing, not quite at it, because the extreme pressure that fills the water column has a slight warming effect on the water itself, a compression-induced thermal property that nudges the freezing point just enough to keep the water liquid at the very bottom. This is not warmth in any meaningful sense. It is the narrow margin between solid and liquid, held by physics rather than by any source of heat. The cold at the trench floor is ancient and completely stable. It has likely not shifted significantly for millions of years. There is no seasonal thermocline reaching this deep, no surface warming penetrating even a fraction of the distance to the floor. The temperature that sits at the bottom of the Mariana Trench today is probably very close to the temperature that sat there in the time of the early mammals, in the time of the first grasses, in the time before the island arc above it had fully formed. It is one of the most stable thermal environments on the planet, not because it is protected, but because nothing that could change it reaches far enough down to touch it. That cold sits in total darkness. Not the dimness of deep water at noon, not the faint blue-gray of the mesopelagic zone, where a sensitive eye might still register something, complete and absolute darkness, the kind that has no gradations, no edges, no moment of adjustment to allow the eye to find its bearings. Sunlight enters the ocean at the surface and begins to lose itself almost immediately. The red wavelengths go first, absorbed within the first few dozen feet of water, draining the underwater world of warmth and color before the depth has even properly begun. Orange follows, then yellow. By 200 feet down, the world is blue and dim. By 1,000 feet, the last blue twilight fades entirely, and below that point, the dark is a single unbroken thing from surface to floor. This transition happens not far from the surface. On the scale of the trench's full depth, the entire 7 miles of the water column below 1,000 feet is not merely dark, but unchangingly, uniformly, perfectly dark. Light never visits. It has never visited. The floor of the Mariana Trench has existed in complete solar darkness since the crust on which it rests was formed, and it will remain in that darkness for as long as the trench endures. In that darkness, the cold does not feel like cold in the way cold is felt at the surface, bracing, immediate, something the body registers as an event and responds to. At the trench floor, the cold is ambient and total, the medium in which everything exists rather than a condition imposed from outside. It is the temperature of the water pressing from above and from all sides, the temperature of the sediment below, the temperature of the dissolved oxygen carried in the deep water as it moved slowly along the ocean floor from its origins in the polar seas where it last touched the atmosphere and sank. That oxygen-carrying bottom water is part of a circulation that operates on a timescale of centuries, moving so slowly through the deep ocean that a parcel of water at the floor of the trench may have last been in contact with the atmosphere 1,000 years ago. It arrived carrying the cold of its origin and holding its oxygen, and it has released that oxygen very gradually to the thin community of life that lives in the permanent dark below. Between the sunlit surface and the permanent dark of the deep, the water passes through a zone where oxygen nearly disappears. This layer sits at a depth of roughly 600 to 3,000 feet below the surface, varying by location and season, and it forms because the organic particles raining down from above attract microbial life as they sink, and that microbial life breathes. It consumes the oxygen dissolved in the surrounding water faster than the slow movement of the ocean can replenish it from above or below. The result is a band of water where oxygen concentration drops to a small fraction of what it is at the surface, low enough that many organisms cannot survive passage through it. Some creatures live their entire lives above or below this band, never crossing it. Others pass through it, only at certain stages of life. The band itself is not static. It pulses slightly with seasonal changes in surface productivity, expanding when more organic matter sinks and more microbial consumption follows, contracting when the supply diminishes. But the deep water below it, the water that eventually fills the trench itself, carries enough dissolved oxygen to sustain life even at the greatest depths, because it entered the deep ocean through a different route, sinking from the surface at high latitudes before the oxygen minimum zone could reach it, and traveling along the floor of the ocean in that cold, dense oxygen-bearing mass. The particles that fall through all of this, through the sunlit zone, through the dimming mesopelags, through the oxygen minimum, and out the other side, through the complete dark of the bathypelagic, and into the cold and pressure of the Hadal water column, are collectively called marine snow. The name fits. In photographs taken by deep-sea cameras, the particles appear as small pale flecks drifting downward through the beam of the light, suspended and slow, moving without apparent direction or intent, taking the path of least resistance as gravity draws them through the water. But they are not water crystals, and they are not falling through air. Each fleck is a fragment of something that was once alive, or that was produced by something alive, or that has been gathered and bound together by the slow physics of aggregation in a dense and living ocean. A fragment of algae broken from a bloom at the surface by a current or a grazing animal. The molted shell of a small crustacean, shed as it grew, transparent as glass and barely denser than the water it falls through. A pellet of digested material produced by a copod, compacted and sinking faster than loose particles would. A string of mucus cast off by a gelatinous organism in the upper water column, already gathering other particles to itself as it descends, becoming a composite object on its way down. From the surface to the floor of the trench, a particle of marine snow may travel for weeks. The rate of fall depends on the particle's density, its shape, whether it aggregates with other particles on the way down, and how much of itself it loses to dissolution or microbial consumption during the descent. Denser particles fall faster. Looser, more irregular ones tumble slowly, catching resistance from the water at every angle. A fecal pellet, compact and relatively dense, may descend at a rate of several hundred feet per day and reach great depths within a few weeks. A loose fragment of algae may take much longer, gathering other material, being consumed in part by bacteria during its fall, arriving at the bottom a smaller and chemically transformed version of what it was when it left the surface. Along the way, through each successive zone of the water column, something is taken from it. The calcium carbonate in the shells of foraminifera and coccoliths, tiny planktonic organisms that build their cases from the ocean's dissolved calcium, begins to dissolve as the particle falls below the depth at which the cold, carbon dioxide-rich water becomes undersaturated with respect to calcium carbonate. This depth, lying at roughly 14,000 feet below the surface, is called the carbonate compensation depth, and below it the calcareous portions of any sinking particle dissolve as reliably as sugar in warm water. What arrives at the floor of the trench has passed through this zone and passed through it slowly enough that anything made of calcium carbonate has been erased. The calcite and aragonite structures, the intricate shells, the elaborate tests, The beautiful, precise geometries are simply gone. What remains is organic material, the siliceous frustules of diatoms, and the skeletal remains of radiolarians, which are built from silica rather than calcium carbonate, and survive the long fall, and clay particles that have no chemistry susceptible to dissolution at any ocean depth. The sediment that results from this process lies across the floor of the trench in a pale, fine-grained layer of remarkable composure. It is largely reddish or brownish clay, material that has been carried across the Pacific by wind and current and delivered to the ocean surface, then sunk slowly over thousands of years to its final resting place. Mixed through this clay are the siliceous remains of organisms, the radiolarians, whose intricate latticed spheres are so fine they pass through the fingers like a dry powder, and the diatoms, whose frustules preserve under the cold with the same quality glass preserves an impression, clear, precise, and permanent. These particles have come from the surface, but they have arrived changed by the journey. They carry within them a chemical record of the water they passed through, the time they spent falling, the organisms that consumed portions of them and left traces of their own metabolism behind. The sediment at the floor of the trench is, in a sense, an archive, not of dramatic events, but of the slow, continuous process of the ocean cycling its own material, downward, renewing the sediment layer at a rate of a few millimeters per 1,000 years. In the center of the trench, in the 3 enclosed basins of Challenger Deep, this sediment accumulates with particular thoroughness. The walls of the trench slope inward, at angles steep enough to send any settled material sliding back down to the floor, and the depth of the basins traps the finest particles that have survived the full descent. A core taken from the deepest sediment, there would pass through layers representing tens of thousands of years of deposition, each thin horizon a record of what the surface ocean was producing at the time, what was living, what was growing, what was dying and sinking. The layers near the bottom of such a core would be physically compressed by the weight above them, their chemistry altered slightly by the pressure and the temperature, their microbial communities ancient and sparse. Near the top, the material would be fresher, the chemistry more active, the organisms more numerous and metabolically livelier, and at the very surface, in the first few millimeters, the sediment is in contact with the bottom water, the cold, oxygen-bearing, pressure-heavy water of the Hadal zone, exchanging chemistry with it constantly, the boundary between the solid trench floor and the liquid water column blurring, at a scale too fine to see. The transition between the sediment and the water is not a clean line. The bottom water just above the floor carries particles so fine they never fully settle, a nepheloid layer, a thin suspension of material that drifts and redistributes with the very gentle near-bottom currents that move through the trench. These currents are weak and slow, driven not by wind or tides, but by the density gradients between water masses, by the slight flow of bottom water along the axis of the trench, by the settling and resuspension of material. They are not currents in the sense of the Gulf Stream or the Kuroshio. There is nothing in the trench to stand in and feel. They are more like a slow inclination of the water, a drift so gentle that particles moved by them take years to travel a few hundred feet. But they are real, and they do work, and they carry the fine organic material that reaches the trench floor across small distances, redistributing it into hollows and depressions in the sediment, building up thicker accumulations in some places than others, creating a topography of food concentration that would matter to anything living on the floor. The oxygen in the bottom water reaches the sediment surface. It moves down into the sediment itself, diffusing slowly through the pore water between grains of clay and silica, being consumed by the microbial life in the sediment as it goes. The depth to which oxygen penetrates the sediment depends on how much organic material is present and how active the microbial communities are. In the trench, where organic material concentrates and microbial activity is real but constrained by the cold, oxygen typically penetrates a centimeter or two into the sediment before being exhausted. Below that depth, the sediment becomes anoxic, devoid of dissolved oxygen, its chemistry governed by other processes, other electron acceptors, other metabolic pathways that have nothing to do with breathing in any ordinary sense. The boundary between the oxygenated upper sediment and the anoxic material below it is called the redox boundary, and it is one of the most chemically active interfaces in the entire trench system. It is invisible, and it is everywhere on the floor, lying just below the surface of the pale clay, like a thin continuous line of transformation, where one chemistry ends and another begins. The darkness above all of this is not empty. The water column of the Hedal zone, between the trench floor and the start of the abyssal plain, several thousand feet above, holds its own particular quality of absence. It is cold through the full extent of that column, cold and dark and still, with nothing to mark the passage from one depth to another except the slow, continuous increase in pressure as the floor approaches. There is no sound source in the trench itself to fill the dark. Sound moves through water more readily than through air and carries farther in the cold, dense water of the deep ocean, but the sources of natural sound in the ocean, cracking ice, breaking surface waves, the calls of animals, are concentrated at and near the surface. What reaches the trench from the surface world is attenuated, filtered, shifted in character by the long journey down. A ship passing overhead might generate a sound detectable at depth, but by the time it reached the floor of the trench, it would have traveled for seconds through miles of water, arriving as a low diffuse signal, stripped of its higher frequencies, faint and sourceless. The deep trench is not truly silent. Nothing in the ocean ever is, but the sounds that reach it arrive as shadows of themselves, distant and altered and stripped of everything that made them recognizable at the surface. Within that muted acoustic world, the water itself carries its pressure and its cold without interruption. The pressure does not propagate as a wave. It simply exists, static, distributed. It has been building since the trench formed, deepening as the Pacific plate continued its slow subduction, stabilizing as the trench approached its current geometry over millions of years. The floor sitting at the base of it has never known anything but this weight, and the water resting on that floor has never known anything but this cold. Temperature and pressure together create a physical environment of extraordinary constancy. The conditions that exist at the bottom of Challenger Deep today are conditions that have existed, with only minor geological variation, for longer than the Alps have been mountains, longer than the Atlantic Ocean has been wide, longer than flowering plants have been a feature of the terrestrial world. The deepest place on Earth is also one of the most stable, not because it is sheltered from change, but because the forces that drive surface variability simply do not reach it. This is the quality of the trench that resists easy comparison. At the surface, even in remote places, the environment shifts. Day follows night, seasons cycle, the temperature of the air and the chemistry of the water change with rainfall, with wind, with the blooms and crashes of the plankton. The deep trench does not cycle. It does not have mornings. The light never changes, because it is never present. The temperature holds within a degree of itself for geologic ages. The pressure is determined by physics, not weather, and physics at this scale does not fluctuate. What this means for anything living there is a world without rhythm imposed from outside. No solar cue, no thermal cue, no cue from the changing chemistry of the water above. Whatever rhythms exist in the deep trench arise from within the organisms themselves, internal timekeepers running without external synchronization, or from the very slow and irregular pulses of organic input arriving from above. A food fall here, a pulse of marine snow following a surface bloom weeks after the bloom has ended. The marine snow arrives unevenly. It comes in greater concentrations after productive periods at the surface, after the spring bloom in the North Pacific, when phytoplankton multiply across vast stretches of sunlit water, and the ocean fills briefly with organic material that then begins its long fall downward. Some of this material reaches the trench floor. The timing is offset by weeks or months from the surface event, delayed by the slowness of the descent, and by the time the pulse arrives at the floor, it is diffuse and widely distributed, a slight increase in the particle concentration of the near bottom water rather than a dramatic event. But it is real, and organisms at the trench floor have evolved to detect it, to aggregate where it concentrates, to extract what energy remains in material that has already been consumed by layer after layer of organisms during its long fall. What arrives at the trench floor is not the rich, lipid-laden organic matter of the surface bloom. It is the residue, the difficult refractory material that nothing else could digest, the siliceous skeletons, the degraded proteins, the fragments of cell wall that resisted every microbial attack on the way down. In the deep cold of the trench, that residue is still food. It is scarce food and slow food, and food that demands specialized biochemistry to access, but it is enough. The rain of particles has been falling since the trench formed, delivering the biological production of the surface ocean downward in continuous small increments, and over the long stretch of the trench's existence, the accumulation is real and dense. The sediment itself is a store of organic material, compressed and transformed by time and pressure, its chemistry altered but not exhausted. Every centimeter of that sediment is a record of past input, and within it, the chemical energy of ancient surface productivity persists, informs that the organisms of the trench floor have, over millions of years, found ways to access. What falls does not fall evenly. The topography of the trench floor, the gently curved basins, the low saddle-like ridges between them, the sloping walls, directs the settling of particles in the same way a bowl directs the settling of dust. The three enclosed basins of Challenger Deep act as funnels. Material that enters the water column above them settles inward as it sinks, the walls guiding it toward the center of each basin, concentrating the organic particles in the deepest portions of the floor. This focusing effect means that the floor of Challenger Deep receives more organic material per unit area than the flat abyssal plain surrounding the trench at 5,000 meters depth. The trench is not only the deepest place, but also a more food-rich environment than the barren abyssal expanses on either side of it. Not rich in the way a shelf or a reef is rich, but noticeably concentrated relative to the surrounding deep ocean floor. The cold holds all of this in suspension. The chemistry of the deep water, its slight alkalinity, its low temperature, its oxygen content, its concentration of dissolved silica and iron and trace metals, is a product of the long mixing of the ocean, of the slow circulation that carries deep water from one part of the globe to another over centuries, of the chemical reactions between seawater and the basaltic rock of the trench walls. This water is old, not ancient in the way the sediment is ancient, but old in the sense of water that has been traveling through the interior of the ocean for a very long time. exchanging chemistry with everything it has passed through, arriving at the floor of the trench, carrying the memory of every environment it has moved through since it last felt sunlight. It is not sterile. It carries dissolved compounds and particles that represent hundreds of thousands of miles of ocean chemistry, compressed into a single cold, dark, pressure-heavy medium. A particle of marine snow drifts through this water at the bottom of the trench. It is very small, smaller than a grain of salt, perhaps, or close to the size of a fine-ground coffee particle, and it is pale, barely distinguishable from the water around it, except in the quality of its density. It has been falling for 3 weeks. It began as part of a phytoplankton bloom at the surface of the North Pacific. A fragment of a diatom cell that was grazed by a copod passed through the copod's digestive system, compacted into a fecal pellet, and released into the water column in a form denser than the original cell. It sank through the sunlit zone, through the oxygen minimum, through the carbonate compensation depth, where the thin calcareous coating it had accumulated dissolved and left the silica frustule beneath. It traveled through the permanent dark of the deep ocean, slowly, gathering other particles, losing a fraction of its organic content with each passing day to the microbial life that attached itself to its surface and consumed what it could. Now it is here, at the bottom, approaching the pale clay of the trench floor. It settles. There is no sound, no displacement. The sediment beneath it does not move. The cold water closes around it in the absolute dark, and the particle comes to rest among other particles very much like itself, pale, silicious, organic, cold, and the floor of the trench receives it as it has received everything else that has ever arrived here, without hurry, without distinction, without memory of anything before. The pressure holds from above, even and total. The temperature does not shift, the dark does not change, and the particle rests in the cold sediment at the bottom of the world, and something in the sediment below it stirs, not quickly, not dramatically, not in any way that can be seen, but stirs and begins very slowly, in the dark and the cold, the long and unhurried work of transformation, taking the particle into itself grain by grain, returning it to the chemistry of the deep ocean, one molecule at a time, the way the trench takes everything that reaches it in the end, gently, completely, and without end. A piece of organic matter comes to rest on the floor of the Mariana Trench, and for a moment the pale sediment around it is still. It did not arrive in any dramatic way. Whatever it was, a fragment of scale, a fragment of something that had once been living far above. It drifted down for weeks through water that grew gradually colder and darker and heavier, losing its shape a little as it fell, acquiring a slow mineral patience. And then it touched the bottom, and the sediment barely moved. The floor of the trench accepted it, the way the floor of any old room accepts what is placed on it, without ceremony, without urgency. And then, within a very short time, the trench began to respond. Chemical signals moved through water the way sound moves through air, not quickly, but reliably, spreading outward in slow invisible gradients from their source. On the trench floor, where there is no light and no current strong enough to carry a leaf, these chemical gradients are the primary news of the world. Something has arrived, something is edible, and in the pale dark of a place where food is scarce and its delivery irregular, this is news worth moving toward. The first amphipods reach the food fall within hours. They are small, pale, curved like a question mark at rest. Crustaceans belonging to the species Hierondelia gigas *, and they are the most abundant large animals in the Hoddle zone. Their bodies are translucent in the way of things that have never needed to hide from light. They move through complete darkness along the gradient of the scent, purposeful in the way of creatures following something real, and they converge on the fallen matter from across the sediment, drawn from distances that would be surprising if the alternative were not simply going without. At foodfall sites like this one, their density can exceed 1,000 individuals across a single square meter of trench floor, a mass of small, efficient, cold-adapted bodies pressed together in the dark around something the surface ocean discarded on its way through. What makes Hyrandelia gigas so well fitted to this place is not only that it tolerates depth, though it tolerates depth at levels that would end most other animal life without negotiation, it is that it eats almost anything. In a trench where food arrives unpredictably and in forms that nothing else has bothered to digest, this is a considerable advantage. The amphipods carry in their bodies a set of enzymes capable of breaking down cellulose, the structural material of wood and plant fiber, which means that when a piece of timber sinks from the surface world, carried down from a river, or broken from a ship, or simply fallen from a coastal tree, these animals can use it. They can take apart the architecture of a forest in the dark at the bottom of the ocean. Wood cellulose is not a food source most animals can access because the molecular bonds holding it together resist ordinary digestion. But Hyrandella gigas produces the necessary chemistry, and so where other scavengers would find nothing of use, these animals find a meal. This is not a recent adaptation. It is the product of deep time working on a lineage that has lived at these depths long enough to develop what the environment required of it. The amphipods feed without light. They navigate without sight, guided by chemical gradients and the slight mechanical disturbances that traveling water makes as another body moves through it. At depth, where darkness is not a temporary condition but the permanent state of things, eyes are an expensive organ to build and maintain. Many heddle animals do not bother, and the ones that do often have eyes reduced to vestigial structures, remnants of a sensory system their ancestors used in shallower water, now only faintly present, like a door in a wall that was bricked up generations ago. Hyrandella gigas. Is among those that have largely set vision aside, and the trench does not require it. In the water column just above the trench floor, a different animal holds its position with a stillness that looks like patience, but is simply how it lives. A snailfish, a member of the genus Pseudoleparus drifts a meter or two above the pale sediment, its body soft and nearly without color, shaped like a comma in the water. It is the deepest living fish known to exist. Nothing with a backbone has been confirmed at greater depth. And looking at it, imagining it in the faint light of a submersible lamp, it does not seem like a fish designed for extremity. It seems, in fact, like a fish that has been gently unmade. There is no swim bladder. Other fish use this gas-filled organ to manage buoyancy, but at Haddle depths, a gas-filled cavity would require so much structural reinforcement to maintain against the pressure that the engineering cost would be prohibitive, and the organ would be useless anyway, since a fish at this depth does not move vertically through any range where buoyancy needs managing in that way. The swim bladder is simply gone. What the snailfish has instead is a body that is more water than tissue, a gelatinous structure in which the pressure outside and the pressure within are not in conflict, because the fluid inside the body is continuous with the fluid outside it. Pressure at this depth passes through the snailfish the way it passes through the water itself. The fish does not resist the ocean. It has become part of what the ocean is made of. The tissue stabilization runs deeper than structure. Inside the cells of Pseudoleparus the proteins that carry out the ordinary chemistry of life The enzymes that catalyze reactions, the structural molecules that give cells their shape, would distort and lose their function under extreme pressure if they were the same proteins that work in a surface fish. Proteins fold into precise three-dimensional shapes, and their function depends entirely on holding those shapes. Pressure destabilizes folds. At 1,000 times the pressure felt at the surface, a protein built for ordinary depths would lose its shape and stop working, and the fish would stop working with it. What the snailfish carries in its tissues is a molecule called trimethylamine oxide, a compound that acts as a counterforce against pressure-induced distortion, stabilizing protein shapes by binding to them in ways that resist the squeeze of the water column above. The deeper the fish, the higher the concentration of trimethylamine oxide in its tissues. There is a limit, somewhere, to how much this molecule can compensate, a depth at which even this stabilization fails, at which no fish anatomy has yet found a solution, and the snailfish may be near that limit, or at it, or just past where another lineage might have found a way through. No fish has been confirmed below roughly 8,000 meters. The deepest confirmed observation of pseudolaparis is not far above that. What lies below, in the final 2 or 3 kilometers of the trench, appears to be a world without fish, a depth that vertebrate life, for all its adaptability, has not reached. The snailfish moves slowly over the sediment, feeding on amphipods and small crustaceans, its body undulating in the cold, still water without any apparent hurry. From above, its outline is barely distinguishable from the dark. From below, against the faint scattered light of any bioluminescent particle drifting past, it would be visible for a moment and then gone. It does not need to be fast. At this depth, with so little food, the most successful strategy is efficiency, burning the minimum of energy for the maximum of return, waiting in the water column for the chemistry of the environment to deliver prey rather than actively pursuing it across large distances. On the sediment not far from where the snailfish holds its position, something much larger and stranger sits without moving. It is pale, roughly circular, and nearly the size of an adult human hand. It looks like a piece of lacework, or like something a tide might leave on a beach, fragile, intricate, built of cemented particles, arranged by a slow intelligence that does not think and yet produces structure. This is a xenophyophore. It is a single cell. The idea that a single cell could grow to this size is one that requires a moment to settle. Most cells are invisible to the naked eye. The cells in a human body are typically a few thousandths of a millimeter across, objects so small that tens of thousands could sit on the period at the end of this sentence. But xenophyophores are not ordinary cells. They are protists, neither animal nor plant, nor fungus nor bacterium, but something else, something that preceded the divergence of all those kingdoms, and they have evolved a cellular architecture that allows them to grow large without dividing into separate cells. The species found in the Mariana Trench, *Syringamina fragilissima *, can exceed 20 centimeters in diameter, a single cell. One continuous volume of cytoplasm, threaded through a self-constructed framework of particles, cemented together by the organism's own secretions, containing many nuclei, but never having divided into separate units the way the cells of a multicellular body do. It is a solution to the problem of being big without being many. The test, the outer structure, is assembled from particles the xenophyophore has gathered from the surrounding sediment. Grains of mineral, fragments of shell, microscopic debris from the long fall of marine snow, all pressed together and fixed into a lattice through which the organism's cytoplasm flows. The result is something that looks constructed, though nothing in the xenophyophore has intentions. It is simply the outward expression of a biological process that takes particles in, incorporates them, and builds outward in the process. The test provides structure. It keeps the cytoplasm from spreading flat across the sediment. It creates an internal geometry of chambers and passages through which the living material of the cell moves and exchanges gases and nutrients with the water around it. And inside the test and around it, and resting on its surface, other organisms make their lives. Nematodes, tiny worms, barely visible without magnification, one of the most abundant animal types in ocean sediments, thread through the chambers of the xenophyophore structure, finding within it a refuge from the open sediment. Polychaeta worms, more substantial in size, take shelter in the larger spaces. Bacteria colonize the surfaces. The xenophyophore, without trying, without knowing, becomes an ecosystem in miniature. A single cell so large that other organisms live inside it the way other organisms live inside a forest. In a trench floor that is otherwise largely flat and uniform, this cell is a structure. It is a complexity. It is a small world across the sediment plain that stretches away from this spot in every direction. The floor of the trench is not a dead place. It does not look busy. In the stillness of the water, and the absolute darkness, and the cold that has not varied measurably in millions of years, nothing announces itself as active or urgent. But movement is here, of a kind that does not announce itself, the slow ingestion of sediment by animals whose bodies have made this their complete way of life. The sea cucumbers of the genera Elpidia, and Piniagoni, are among the most visible animals on the trench floor when a light is brought near. They are holothurians, relatives of sea urchins and starfish, but soft-bodied, elongated, and modest in a way their spiny cousins are not. They move across the sediment with a slow muscular undulation, drawing the pale material into their digestive tracts and extracting whatever organic content it holds, particles of marine snow that have settled there, fragments of bacterial mat, the chemical traces of things that fell and dissolved and left their carbon in the sediment. They are eating the floor. This strategy, sediment ingestion, is not intellectually glamorous, but it works. The trench floor is covered with organic material that has traveled thousands of meters to get there. Much of it is no longer easily recognizable as food. The calcareous shells of surface organisms have dissolved before they arrived. The soft organic components of marine snow particles have been partially degraded by bacteria during the long fall. What reaches the sediment is a mixture of fine clay and the siliceous remains of organisms whose glass-like skeletons survived the pressure and the chemistry of the descent. Diatoms, radiolarians, and a residue of organic carbon, too dilute to extract efficiently, except by moving a great deal of sediment through a digestive system designed for exactly that purpose. The holothurians move slowly. They eat constantly. Over their lifetimes, they process volumes of sediment that would be difficult to imagine in a more active organism, but at this depth, slow and constant is the available mode, and it is enough. Some members of Piniagoni, though, do something that still draws attention from researchers who observe it. They lift off the sediment. They hold their elongated bodies horizontal in the water, or turn upside down, or actually swim, with a slow undulating movement of their body walls. In the water a few centimeters, or sometimes a meter above the floor. This swimming is not vigorous, It is barely swimming at all by any surface standard, but it is unmistakably locomotion in the water column rather than on the sediment, and the reason it happens is not fully settled. The best current thinking is that it allows them to sample a wider area of sediment surface than crawling would permit, or that it helps them navigate toward foodfall sites by moving in the near bottom water where chemical gradients from decomposing matter travel most efficiently. A sea cucumber swimming in the dark above the floor of the deepest trench on Earth, upside down, in water 2 degrees above freezing, half a mile below the lowest point most submarines ever reach. The image holds a particular kind of quiet strangeness, not the strangeness of something threatening, but of something that simply found a way through, on its own terms, in its own time. The sediment itself, the pale, fine material that covers the floor of the trench to depths of many meters, is not inert. It only appears to be. Pick up a cubic centimeter of it, a volume smaller than a sugar cube, taken from the upper few millimeters of the trench floor where organic input is freshest, and within that small cold space are hundreds of millions of microbial cells, alive, metabolizing, doing the chemistry of life in total darkness, under pressure that nothing made of dry land can sustain. These are not the bacteria of soil or skin or gut, though they are distant relatives of all those things. They are organisms shaped by this specific place over timescales that make human civilization vanishingly brief. They are piezophiles, pressure-loving, or more precisely, pressure-requiring, and the conditions that would kill a surface bacterium in minutes are the conditions under which these organisms function best. The enzymes they carry have been refined by selection to hold their shapes at pressures above 700 bars. Their cell membranes, which in a surface bacterium would stiffen and lose function under compression, are enriched with polyunsaturated fatty acids that remain fluid under the squeeze of extreme depth. The same general principle by which deep-sea fish use particular lipids to keep their membranes working, arrived at independently by organisms separated by hundreds of millions of years of evolution, because the physics of the problem was the same and the chemistry settled on a similar solution. What these bacteria do for energy does not involve sunlight. At the surface, almost all life ultimately runs on sunlight, fixed by plants and algae through photosynthesis, and then passed through food webs until it reaches the last consumer. At the floor of the Mariana Trench, sunlight is not a concept that has any practical relevance. The light that falls on the Pacific Ocean above the trench is 11 kilometers away. The bacteria in the sediment have never been near it. Instead, they are chemolithotrophs, organisms that extract energy from chemical reactions involving inorganic compounds. One organism oxidizes ammonia and releases energy in the process. Another takes hydrogen and uses it to drive its metabolism. Others process iron, or sulfur, or manganese, drawing on the slow chemical differences between compounds in different oxidation states, the way a surface organism draws on the difference between sunlight and darkness. This is not an inferior or primitive way of life. It is a way of life that predates photosynthesis, that was running in the ocean before there was any oxygen in the atmosphere, that has continued without interruption through every geological upheaval of the last several billion years. It does not need the sun. It does not know the sun exists. It is simply busy, in the cold, in the dark, in the sediment, turning chemistry into life. The diversity of these microbial communities is genuinely large, though the tools required to assess it fully were not available until recently, and each new sampling expedition tends to find lineages that have not been described before. The trench sediments contain organisms that belong to groups common in other ocean habitats, but also organisms that appear to be entirely specific to hadal environments, lineages that diverged from their relatives when the trench formed, or were isolated in it over millions of years as the plate continued its descent and the trench deepened, and that have been refining themselves in this specific pressure and chemistry and cold ever since. When sediment from the Mariana Trench is brought to a laboratory and cultured, some of the organisms that grow do so only under high pressure. Release the pressure and they stop. They cannot tolerate the world outside their own. They are as specific to this place as the trench is specific to this planet. The oxygen these microbes use does not come from photosynthesis happening nearby. It arrives from the deep ocean circulation, cold water masses that formed at high latitudes, sinking because cold, dense water falls, traveling along the floor of the Pacific Basin for centuries before reaching the trench, still carrying dissolved oxygen from the atmosphere it was in contact with at the surface. This is one of the stranger facts about the deep ocean, that the oxygen keeping aerobic life alive at the floor of the Mariana Trench entered the water somewhere in the high latitude North Pacific or Antarctic centuries ago, when the water was cold enough to hold it and dense enough to sink, and has been traveling in the dark ever since, carried in the water itself as a dissolved gas, until it arrives here in the trench and passes into the cells of an organism that has never been anywhere else and will never leave. The trench floor is not uniform. It has its own geography, low ridges that divide the deepest basins from one another, slight depressions where sediment accumulates more thickly, areas near the walls where material tumbles down and disturbs whatever was living there, flatter stretches away from those disturbances where the sediment surface has not been broken for a long time, and the communities within it are old and continuous. In the flatter regions, the sediment layers beneath the surface record depth in time. The top layer is most recent, and the layers below it descend through centuries, and then millennia of accumulated fall. A core taken from the floor, pulled out as a cylinder of pale material, holds in its layered strata the chemical record of what the surface ocean was doing when those particles fell. The balance of species whose shells are preserved there, the isotopic composition of the carbon, the trace metals absorbed from the water, a long, slow diary of the ocean's history, written in sediment in the deepest room the ocean has. The walls of the trench above the floor carry their own inhabitants. On steep rock surfaces where sediment cannot accumulate easily, other communities have established themselves, organisms that anchor to hard substrate and filter the passing water, or that graze the thin films of bacteria growing on exposed rock. The walls drop away from the surrounding seafloor at steep angles, in some places as steep as any mountain face, and the rock is deformed by the forces that created the trench, compressed and sheared and fractured along the lines where the Pacific plate bent downward, producing surfaces that range from broad, smooth expanses of ancient basalt to fractured ledges and overhangs where the rock is broken along fault lines and tilted. On those surfaces, life has arrived and stayed in the way that life tends to, not by planning, but by the simple mathematics of what survived the conditions and what did not. Moving back across the floor, toward the shallower margins of the trench, where the walls begin their long ascent back to the abyssal plain, the sediment thickens and the population density of the larger animals increases somewhat, because the food input from the water above is slightly richer here, gathered and directed by the trench's own topography. The trench is, in one sense, a collector, a funnel in the seafloor that concentrates the output of the surface ocean above it and channels it downward to where these animals and microbes wait. The organic carbon that enters the trench from above is not evenly spread. It gathers in the deepest parts, channeled by the geometry of the walls, and so the floor of the trench is richer than the abyssal plain outside it, in proportion to the depth of the funnel above. This concentration effect means the trench supports more life per unit of seafloor area than the flat, deep ocean beyond its walls, an irony of a kind in a place associated with absence and desolation. The xenophyophore rests on the sediment in the pale light of an imaginary lamp, its lattice structure faintly luminous against the dark, the cytoplasm within it moving in ways too slow to watch in real time, each nucleus carrying the same genetic instructions and yet contributing to a single coherent organism that has lived here alone and complete, for a time that cannot be easily estimated. Around it, nematodes the width of a thread move through the chambers of the test. On the sediment nearby, two amphipods are feeding on the residue of the food fall that attracted the earlier mass gathering, working at the final traces with a thoroughness that leaves nothing behind. The snailfish has moved away, or is resting somewhere in the dark water above, or has found another feeding area where amphipods are more concentrated. The sea cucumbers move slowly across the sediment at the pace of organisms that have no reason to hurry, drawing the pale floor through their bodies and returning it, changed behind them. The darkness here has a quality of completeness that daylight darkness never quite achieves. Even in a room with every light off and curtains drawn, there are photons from electronics, from the faint luminosity of paint, from the crack under a door. Here, 11 kilometers below the surface, the last photon from the sun was absorbed before the water reached a depth of 200 meters, 9 kilometers, and more above this floor. The darkness is not the absence of enough light, it is the total absence of all solar light. What exists here in its place is chemical, the occasional faint glow of a bioluminescent organism passing through, a brief flash that registers in no eye at this depth, because nothing at this depth depends on eyes for its orientation. The darkness is old. It has been continuous in this trench for as long as the trench has been this deep, which is tens of millions of years. The organisms here were not plunged into darkness. They evolved into it over so many generations that the count has no practical meaning until darkness became not an obstacle, but the medium in which all of their chemistry and behavior and structure are expressed. The cold is similar in its completeness. A degree or two above freezing, held steady by the weight of water above and the slow circulation of deep ocean currents, varying by almost nothing across seasons, that the trench has no way of knowing or happening, maintained at this temperature since long before there were animals large enough to feel it. The organisms here do not experience the cold as cold. They experience it as the temperature of the world, the only temperature their enzymes are built to function in, the temperature at which their cell membranes hold the right fluidity, the temperature that their metabolic rates are calibrated for. Bring them to the surface, and the warmth would be as destructive as the pressure would be, a set of conditions as foreign and as fatal as hard vacuum is to a surface organism. Everything at this depth is calibrated to this depth. That is the plain fact of adaptation taken to its logical end, not calibrated to survive here in the way of an organism managing a difficult environment, but calibrated to belong here, to function best here, to be less than fully functional anywhere else. The Hadal Zone is not a harsh environment that's selected for tough organisms. It is a consistent environment that's selected for specific organisms. The toughness is a quality projected onto it by comparison with the surface. From inside the trench, there is only the world as it is. In the sediment beneath the foodfall site, where the amphipods have been feeding, the microbial community is already responding to the input of fresh organic material. Cells that were cycling slowly through the available substrates in the undisturbed sediment have encountered new carbon, and their metabolic rates are rising as the chemistry of the local environment shifts. This response will continue for weeks or months as the organic matter is broken down and incorporated and returned to the water column as dissolved compounds, the carbon recycled once more, the nitrogen and phosphorus distributed, the energy released that the original organism captured in sunlight at the surface, passed now through the gut contents of amphipods and the metabolic pathways of microbes in the cold sediment at the bottom of the world. The food fall is nearly gone now. The amphipods have thinned as the chemical gradient diminishes and the last material is incorporated. The trench floor settles back to its characteristic stillness. A xenophidiophore 2 meters away has not moved and will not move. It does not move, not in any self-directed sense. The sea cucumbers continue their slow traversal of the sediment, with the unhurried continuity of things that eat what the floor provides, and ask nothing more of the world than that. In the water above, the snailfish drifts in the cold, suspended in a medium that is indistinguishable from itself, waiting for the next chemical signal that means food, waiting in the way of creatures for whom patience is not a virtue, but simply the shape that time takes. In the sediment, in every direction from this spot, and extending across the floor of the trench for kilometers, the microbes continue their work without interruption. They have been doing this for millions of years. The specific cells alive right now have been alive for hours or days. Microbial generations are short, but the lineages they belong to, the genetic sequences they carry, the metabolic pathways they run, these are old. Some of the enzymes active in these cells have close relatives in organisms that lived before the trench existed, before the Pacific Plate reached this part of its descent, before the deep sea floor of this part of the ocean was laid down. The chemistry being performed right now in the cold sediment under 11 kilometers of water is ancient chemistry. The organisms performing it are the most recent expression of a line that stretches back without visible break to the earliest ecosystems the ocean has held. They do not know any of this. They are not aware of anything. They metabolize, they divide, they die, and their molecular components are taken up by other microbes, and the cycle turns in the darkness with a quiet completeness that does not require any awareness of itself to continue. The floor of the trench is still. The food fall is gone. The amphipods have dispersed back into the surrounding sediment, following whatever gradients the cold water carries to them. The snailfish is somewhere in the dark above, or resting on the sediment somewhere along the trench, its translucent body releasing no signal that would attract a predator, because at this depth there are few predators for something its size and none that hunt by sight. The xenophyophore sits in the cold and the dark as it has always sat, its single vast cell conducting its chemistry, sheltering its community of small lives within its self-built structure, belonging to this place with a completeness that nothing brought in from outside ever fully achieves. And beneath the surface of the sediment, in the first few millimeters, and then in the layers below, hundreds of millions of cells in every cubic centimeter are doing the work that keeps this ecosystem running, cycling carbon, fixing nitrogen, oxidizing metals, maintaining the chemical conditions that allow every other form of life in the trench to persist. They are invisible. They are present everywhere. They have been here longer than the animals above them, longer than the trench walls have held their current shape, longer than any visible organism in this water. And in the still cold dark of the deepest place on Earth, with 11 kilometers of ocean pressing gently down on the sediment above them, they continue. On the 23rd of January, 1960, the water closed over the Trieste, and the surface disappeared, not all at once. The light thinned first, the bright chop of the western Pacific giving way to a deep surrounding blue that pressed in from every direction at once, and the two men sealed inside the small sphere of steel. One American naval officer, one Swiss oceanographer, had only the instruments in front of them and the slow, deliberate creaking of the hull to tell them where they were going, down at roughly 2 feet per second into the longest descent any human beings had yet attempted. The Trieste was not built for speed or elegance. It was a bathyscaphe, a word that means deep boat, and it looked more like a blimp or a whale than anything built for grace. A large float filled with aviation gasoline sat above the pressure sphere, providing buoyancy, and iron-shot weights were held in place by electromagnets, ready to be released to slow the descent or begin the rise. The sphere itself was barely 5 feet across. Two men in 5 feet of sphere, descending 11 kilometers into the ocean, is not a comfortable arrangement. It is, however, a determined one. The descent took 4 hours and 47 minutes. The instruments ticked. The water darkened. Below 200 meters, the last stain of blue withdrew, and the ocean outside the single viewport became the color of nothing at all. Temperature gauges registered the cold coming in through layers of the water column. Pressure gauges tracked the increasing weight of the ocean above. The men ate chocolate and waited, which is most of what diving in the deep ocean has always required of the people who attempt it. There is no sensation of falling in a slow dive. The vessel does not plummet. It settles the way a leaf settles through still air, not urgently, not with anything resembling drama, but with a kind of patient inevitability. The ocean accepted the Trieste, the way it accepts everything that enters it, without response, without ceremony, in the same absolute dark it has maintained at these depths for longer than there have been animals with eyes. At 10 kilometers, the water pressure outside the hull had exceeded 1,000 times the pressure of the air at the ocean's surface. A sealed metal drum at that depth would crumple inward in the first fraction of a second. The sphere holding Don Walsh and Jacques Picard had been engineered for exactly this. Walls of steel 5 inches thick, tapered and reinforced and calculated to hold, but no engineering is entirely without feeling. The hull made sounds on the way down. One of them partway through the descent was a sharp crack, loud enough to alarm both men. They checked the instruments. Nothing had failed. The outer plexiglass window of the entry tube had fractured under the pressure, leaving the inner window and the sphere itself intact. They continued down. The bottom arrived without announcement. The sediment outside the viewport rose briefly in a pale cloud, fine, white, composed largely of the siliceous remains of small sea creatures that had spent tens of millions of years accumulating in this place, and then settled again, and the two men looked out through the thick glass at the floor of the world's deepest trench. They had 20 minutes before the ascent needed to begin, so that the battery reserves would last the return. Picard later reported seeing a flatfish resting on the sediment outside the viewport, a pale creature lying still in the wash of the Trieste's, light, apparently unbothered by the presence of a steel sphere that had arrived in its neighborhood for the first and last time. Scientists later debated whether what he saw was truly a fish of the kind that lives near coasts and shallow water, or something else, A sea cucumber, perhaps, or a holothurian, or simply the product of strained eyes and low light after 5 hours of descent. The uncertainty has never been fully resolved. What is certain is that the bottom was not empty. Something was there. 20 minutes on the bottom. Then the weights released, the iron shot fell away, and the asterisk Trieste asterisk began the long climb back toward the surface, toward light, toward the air, and the deck of the support vessel, and the particular warmth of a Pacific morning, above 11 kilometers of cold water. The whole dive, descent, bottom time, and ascent lasted 9 hours. It was by most measures one of the more disciplined acts of human curiosity of the 20th century. Years of engineering and logistics and planning compressed into 9 hours in the dark for 20 minutes on the floor. For more than half a century after that dive, no human being returned. The trench floor lay undisturbed, in the way that places where no one goes lie undisturbed, which is to say, not truly undisturbed at all, because the ocean is always moving, the sediment is always accumulating, and the organisms living in the pale silt had no idea the asterisk Trieste asterisk had been there, or any way to record that it had gone. The bottom continued, the pressure continued, the cold continued, the fine, slow drift of organic particles from the surface continued to fall, as it had been falling for longer than there have been people to observe it. In March of 2012, a vehicle descended into Challenger Deep for the first time in 52 years. It looked almost nothing like the asterisk Trieste asterisk, where the bathyscaphe had been squat and wide. The asterisk Deep Sea Challenger asterisk was narrow, designed to move vertically through the water column rather than horizontally, shaped more like a torpedo than a boat, painted a particular shade of iridescent green that was visible to cameras but would mean nothing at all in the dark below 1,000 meters. It carried one person. James Cameron, the filmmaker, had spent years in collaboration with engineers in Australia, developing a craft capable of reaching the bottom and staying there long enough to document what it found. The descent in the asterisk Deep Sea Challenger asterisk took 2 hours and 36 minutes. The craft dropped at a rate of roughly 500 meters per hour, faster than the asterisk Trieste asterisk had managed, its exterior cameras recording the transition from the pale blue of the shallower ocean through the gathering dark of the mesopelagic zone and into the absolute black below. The cameras saw nothing living during the descent, or rather, they recorded the water, which showed nothing. Life at those depths is not absent, but it is sparse and small, and not inclined to gather at the edge of a passing light. Cameron spent approximately 3 hours on the bottom. He collected sediment samples, documented temperature and salinity readings, and filmed with high-definition cameras the sediment floor and the water column just above it. The footage was later broadcast and studied. What it showed was, in one sense, a great deal, a landscape of pale, near-featureless sediment stretching away from the craft's lights in every direction, the occasional particle drifting slowly through the water column, the texture of the floor varying only slightly from one frame to the next. In another sense, what it showed was how much the trench floor resists being seen from a small, bright-lit craft that arrives and departs in the space of a few hours. The manipulator arm collected material, the sediment samplers operated, the instruments recorded, and then the buoyancy systems engaged, and the asterisk Deep Sea Challenger asterisk rose back toward the surface, and the floor of Challenger Deep returned to the condition it maintains for all but the most occasional and brief exceptions: dark, cold, patient, undisturbed. There is a quality to these dives that the records of them can only partially convey. The instruments measure pressure and temperature and salinity with perfect fidelity. The cameras record light and form, but neither the instruments nor the cameras can record what it is to be a human being inside a small sealed vessel at a depth where the water column above is nearly 7 miles tall, to sit with the full weight of the Pacific Ocean pressing in from every surface, and to look out through a thick glass port at a place no sunlight has ever reached, and to register, in whatever way the body registers such things, the sheer scale of the space that surrounds you and extends in every direction without any boundary you could find or name. The men and the women who have made these dives describe it differently. Some speak of stillness, some speak of the narrowness of the craft and the completeness of the dark. Some describe an absorbed, professional focus on the instruments and the task. The experience resists reduction, which is perhaps appropriate for a place that resists the kind of comprehension that requires daylight. The Five Deeps expedition arrived at Challenger Deep in the spring of 2019. Victor Vescovo, a retired naval officer and private investor, had spent years working with the company Caladan Oceanic and the engineering team at Triton Submarines to build a vessel capable not only of reaching the deepest points of all 5 of the world's oceans, but of doing so repeatedly and reliably, a craft that could descend multiple times rather than serving as a one-time demonstration. The Asterisk DSV limiting factor. Asterisk was that craft, a white 2-person submersible with a pressure hull of specially formulated steel, built to withstand repeated dives to all depths without degradation to its structural integrity. On the 1st of May, 2019, Vescovo descended alone to a confirmed depth of 10,928 meters in the eastern pool of Challenger Deep, setting a new record for the deepest crewed dive in history. The descent took roughly 3.5 hours. The ascent took roughly 4. The time on the bottom was several hours, more than any previous crewed dive, long enough for extended observation and sampling. What the dive found, along with new topographic data and biological and chemical samples, was a plastic bag on the seafloor. The detail was noted in the expedition's scientific reports and received considerable attention. A plastic bag at nearly 11 kilometers depth in the most remote and inaccessible ocean environment on Earth. It had arrived the way everything arrives at the trench floor, settling through the water column from somewhere far above, carried by currents and the slow gravitational pull of density and depth. It was not alone. Vescov and the expedition's science team documented other artificial material on the floor during multiple dives: candy wrappers, other plastic fragments, evidence of materials manufactured at the surface and distributed through the ocean system with sufficient thoroughness to reach the bottom of Challenger Deep. The trench is remote, it is not separate. The Five Deeps expedition also carried out a multi-beam sonar survey of Challenger Deep and the surrounding trench topography during the same period of operations, using equipment mounted on the surface support ship. The survey resolved the 3-basin structure of Challenger Deep, the eastern, central, and western pools, at horizontal resolutions approaching 25 to 50 meters, mapping the shape of the trench floor and its surrounding walls with a precision no previous survey had achieved. Multi-beam sonar works by sending a fan-shaped array of sound pulses downward from a ship's hull. The pulses travel down through the water column, more than 10 kilometers in the case of Challenger Deep, and when they reach the seafloor, they reflect and return. The time between transmission and return, combined with the known speed of sound through water, gives the distance to the floor at each point in the fan. The ship moves forward, the fan sweeps continuously, and the returning signals build into a 3-dimensional picture of the seafloor below. It is a slow process, The ship must travel at modest speed to allow the pulses time to descend and return before the next array fires. But over hours and days of surveying, the picture accumulates. The result of that survey was a map. Not a perfect map. The resolution at those depths cannot match what aerial photography provides of a mountain range, but a map with genuine precision, enough to see the three basins and the saddle-like ridges separating them, the steep walls dropping from the surrounding abyssal plain, the slight variations in depth across the trench floor. A map drawn not with light, but with sound, each data point an echo from a place 11 kilometers below the surface of the ocean, a place that has never been lit by anything other than a submersible's lights in the whole of its existence. There is something particular about a map drawn from echoes. It is in a literal sense a picture made from absence, from the interval between a sound sent out and a sound returned, the gap that represents all that distance of cold water and dark. The shape of the bottom is inferred, calculated, assembled from time. The floor of Challenger Deep was never seen by the multi-beam array. It was heard in the way that a bat hears a wall or a moth hears a bat, not through light, but through the return of a signal sent into the dark. The wire soundings that gave Challenger Deep its first measured depth came from the original voyage of HMS Challenger. The British naval vessel that spent more than 3.5 years crossing the world's oceans between 1872 and 1876, dropping a weighted line over the side and measuring how far it went before the tension changed. The expedition was the first systematic attempt to measure and sample the ocean at depth. In August of 1875, somewhere in the western Pacific, a sounding returned a depth of approximately 4,500 fathoms, more than 8 kilometers, deeper than any ocean measurement previously recorded, and deep enough to give the place a name that would eventually become the most famous depth measurement in oceanography. The Challenger expedition. Scientists had no way to know they had found the deepest point on Earth. They had no way to know, for that matter, that what they were measuring was the bottom of a subduction trench, because the concept of subduction, of tectonic plates descending into the mantle at convergent boundaries, would not exist for nearly another century. They dropped the line. They measured the return. They recorded the number. They moved on. The world changed considerably in the decades that followed, and the number they recorded that day in 1875 remained on the map, marking a place that subsequent technology would verify, refine, and eventually visit in person. Between the original wire soundings of the Challenger and the multi-beam surveys of the Five Deeps expedition, there are more than 100 years of increasing precision. Wire to sonar, broad estimate to detailed map, single depth reading to three-dimensional topographic model. The shape of the deepest place on Earth became better known in increments, each instrument more capable than the last, each survey revealing features the previous one had missed. The ROV Kaiko a Japanese remotely operated vehicle, developed and operated by the Japan Agency for Marine Earth Science and Technology, reached the bottom of Challenger Deep in March of 1995, 35 years after the Trieste Kaiko was not crewed. It descended on a tether from a surface support ship carrying cameras, sampling tools, and sensors, and it returned to the surface carrying something the Trieste could not have brought back: sediment cores from the trench floor. Those cores were cylinders of pale, cold material, no wider than a human forearm, collected from the upper layers of the trench sediment. Inside them were microbial cells, preserved in the cold and the pressure, representing communities that had been living at those depths for time spans no instrument on the vessel could measure directly. The samples were returned to the surface and analyzed in laboratories, and what emerged from that analysis was, among other things, the first direct confirmation that active microbial metabolism was occurring at the maximum depth of Challenger Deep, that even at the furthest point from the sunlit surface, in the coldest and most pressured water in the ocean, life was processing, consuming, transforming. The Keiko continued operating for nearly a decade, making multiple dives and returning sediment and water samples from various depths in the Mariana Trench. In May of 2003, during recovery operations in rough seas, the vehicle was lost. A tether failure during a surface storm sent it to the bottom of the sea. Not Challenger Deep, but the Pacific. It was never recovered. The scientific record it built, however, was substantial, and the microbial species and chemical signatures it helped identify from the trench floor became foundational to subsequent work on Hadal ecology. A later vehicle, the hybrid remotely operated vehicle, Nereus *, built by the Woods Hole Oceanographic Institution in the United States, extended the biological and chemical sampling record further. Nereus * could operate both on a tether and as a free-swimming autonomous vehicle, giving it flexibility that previous ROVs lacked. It reached the bottom of Challenger Deep in May of 2009 and returned samples that added to the growing picture of microbial diversity at Hadal depths. In May of 2014, during operations in the Kermadec Trench to the east of New Zealand, Nereus * imploded at depth, the pressure finally overwhelming the vehicle's structural integrity in a moment that produced no drama visible at the surface, only the sudden absence of a signal on the tracking systems aboard the support ship above. The loss of Nereus * was a significant setback for deep ocean research. It was also, in a quiet way, a demonstration of the scale of what the instruments are working against. The pressure at Hadal depths is not a hostile force with any intention toward the things that enter the trench. It is simply the physical consequence of 11 kilometers of water exerting its weight downward. It does not distinguish between the organisms that have evolved over millions of years to accommodate it and the vehicles humans have engineered to resist it. It is patient in the way that physics is patient. It applies its force continuously and without variation, and whatever structure does not accommodate it will, in time, fail. The crewed dives are in this sense a different kind of test than the ROV deployments. A robotic vehicle lost at depth is a loss of equipment and data. A crewed vehicle is something else. The engineers who designed the Trieste *, the Deep Sea Challenger *, and the DSV limiting factor * understood this, which is why the pressure spheres were built to margins well beyond the minimum required, and why the descent and ascent procedures were planned and tested and rehearsed before any of the vehicles entered the water over Challenger Deep. The history of deep ocean diving is largely a history of careful preparation, meeting conditions that could not be entirely anticipated, and in the cases that mattered most, the preparation winning. Victor Vescovo made several dives in Challenger Deep during the Five Deeps expedition, not one. This was by design part of the expedition's scientific value. Repeated access to the same location allowed for comparative sampling across different sessions, and the DSV limiting factor had been built specifically to support this kind of multi-dive program. Between his dives and those of expedition scientists who accompanied him on later descents, the team accumulated more bottom time in Challenger Deep than all previous crewed dives combined. The support infrastructure for a crewed deep dive is considerably larger than the dive itself suggests. Above the *DSV, limiting factor during each descent, the support ship *DSSV, pressure drop maintained position using dynamic positioning systems, holding its location against ocean currents with continuous adjustments to its propulsion. Acoustic tracking systems monitored the submersible's position and depth in real time. Communication links, limited by the physics of sound transmission through water, which carries acoustic signals but not radio, allowed the vessel and the submersible to exchange basic information during the dive. Recovery teams stood ready for the ascent. The ascent of a deep submersible is in many respects more challenging than the descent. The ballast drop begins the rise, but the vehicle's buoyancy and speed must be managed through the entire return journey, and the transition from the near-freezing water of the Hadal zone back through the thermoclines of the mid-ocean to the surface involves physical stresses on the structure that differ from those of the descent. At the surface, the submersible must be located. It surfaces without precise GPS, since GPS signals do not penetrate water and must be found by the ship using the acoustic pinger and visual spotters scanning the surrounding ocean. Then the vehicle must be lifted from the water, in whatever sea conditions prevail, by a crane and crew that have done it before and know exactly how it can go wrong. After each successful ascent, the instruments were downloaded, the samples were cataloged, and the data from the multi-beam sonar surveys continued to accumulate on the ship's servers. The shape of the deepest place on Earth was becoming, incrementally and with considerable effort, something that could be seen. The three basins of Challenger Deep, the eastern, central, and western pools, lie along a roughly east-west axis, each separated from the next by a saddle of slightly shallower ground where the trench floor rises a little before falling again. The eastern pool is the deepest, reaching the confirmed maximum of 10,928 meters at the point Vescovo reached in 2019. The central and western pools are somewhat shallower, a relative term, since all three lie well below 10,000 meters, and together the three basins constitute the full extent of what is technically Challenger Deep, a region occupying perhaps 10 to 12 kilometers of the trench's total length of more than 2,500 kilometers. The first multi-beam surveys of the Mariana Trench were carried out in the 1990s, and they revealed the basic structure of the trench's floor and walls. But the equipment available then produced resolutions considerably coarser than those of the 5 Deep's expedition survey, and the finer internal structure of Challenger Deep, the precise shapes of the three basins, and the ridges between them remained partly ambiguous until the more recent surveys resolved it. The picture continued to improve with each generation of sonar technology, each improvement in the processing algorithms used to convert raw acoustic data into depth measurements, each new survey that crossed the same ground at a slightly different angle. This is, in miniature, the story of how humans have come to know the deep ocean, not through a single discovery, not through any single dive or expedition, but through an accumulation of readings and samples and surveys, each one adding a small piece to a picture that has been building for 150 years and is still nowhere near complete. The original wire soundings of the Challenger established that the deep ocean existed and had a measurable bottom. The subsequent echo soundings of the mid-20th century began to reveal its shape. The first crude dives confirmed that the bottom could be reached and was not empty. The ROV deployments brought back samples. The modern multi-beam surveys provided the highest resolution maps yet made, and still the trench contains more than any of these instruments have yet resolved. Sound travels well in water, It travels, in fact, considerably better than it travels in air, faster, over longer distances, with less attenuation at the frequencies useful for acoustic communication and sensing. This is why multi-beam sonar works at all at the depths of Challenger Deep. The pulses sent from the surface ship have enough energy and coherence to travel 11 kilometers down, reflect from the seafloor, and return 11 kilometers up as detectable signals. It is also why the hydrophones placed in the Mariana Trench in 2014 picked up not just the geological sounds of the trench itself, the low creaking of the crust, the occasional passage of a seismic wave from somewhere along the subduction zone, but the sounds of the surface world transmitted downward through 11 kilometers of water. The hydrophones recorded whale calls. They recorded distant earthquakes. They recorded the engine noise of ships on the surface, the propeller signatures of vessels passing hundreds of miles away, transmitted to the deepest point in the ocean by the efficient acoustic medium of the water column. And they recorded the low, slow pressure signature of a Category 4 typhoon passing directly overhead, the waves and the wind and the barometric chaos of the storm reaching all the way to the trench floor as a deep acoustic pulse, the weather of the surface world arriving without any diminution of its essential identity in the silence of the deep. That the deepest place on Earth is acoustically connected to the surface is not perhaps a surprise to those who work in ocean acoustics. Sound has always traveled well in water, but there is something in the image that settles gently. 11 kilometers of ocean, cold and dark, and under a pressure that would destroy any unsupported structure. And yet at the bottom of all of it, a microphone hears the storm above. The trench is not sealed. It is not separate. It opens upward as surely as it closes downward, and the sounds of the world above travel into it continuously. The relationship between the trench and the surface world is not only acoustic, it is chemical, biological, and physical in ways that the history of deep ocean research has gradually made clearer. The organic particles that fall from the sunlit ocean to the trench floor carry with them not only the carbon and nitrogen and phosphorus of surface ocean productivity, but also whatever is dissolved or suspended in the surface ocean at the time of their formation. This includes, in the present era, synthetic compounds that did not exist in the ocean before the mid-20th century. The plastic bag that Vescovo found on the floor of Challenger Deep was a visible example of this. The polychlorinated biphenyls detected in the tissues of amphipods collected from the trench floor were a chemical one, invisible, measured only by laboratory analysis of the organisms after recovery, but present in quantities that spoke to the efficiency with which the ocean concentrates certain persistent compounds in deep-sea sediments and the animals that feed on them. The trench receives what the ocean sends, and the ocean receives what the land and the atmosphere provide. In the spring of 2019, after the 5 Deeps expedition's Challenger deep dives were complete, the *DSSV pressure drop asterisk moved on toward the next of the 5 target locations, the deepest points of the Atlantic, Indian, Arctic, and Southern Oceans. The Mariana Trench remained as it had been before the expedition arrived, 11 kilometers deep, cold, dark, under a pressure that has not meaningfully changed in longer than human civilization has existed, inhabited by organisms that have adapted to those conditions over spans of time the expedition's records cannot encompass. The instruments came and went. The trench stayed. There is something to be found in that contrast. The Trieste asterisk, the Deep Sea Challenger asterisk, the DSV limiting factor asterisk, the Keiko asterisk, the Nereus each one arrived with its instruments and its samples and its lights and its brief period of operation, and each one left. The trench remained. The pale sediment continued to accumulate. The amphipods continued to move across it in the dark. The microbial communities in the upper layers of the sediment continued to process the organic material settling from above, as they had been processing it long before any of the vehicles existed or were imagined. The knowledge that the expeditions returned was real and hard-won and permanently part of the record. Walsh and Picard proved the bottom could be reached. Cameron demonstrated that crude systems could operate there for hours with sufficient instrumentation. Vescovo confirmed the deepest point with precision and documented the trench's three-basin structure from the inside. The ROVs brought back material from the floor. The sonar surveys built the map. Each expedition extended what was known, and each one found, in the process, that what remained unknown was at least as large as what had been resolved. The shape of Challenger Deep is known now to a resolution of a few tens of meters, drawn in echoes by instruments moving slowly across the ocean surface above. The three basins lie in their sequence along the trench floor, each one a submerged depression in the deepest place on Earth, separated by low ridges of sediment and deformed rock that rise just slightly above the otherwise flat bottom, a landscape that no sunlight will ever reach, and that the handful of human beings who have descended into it saw only in the narrow beam of their craft's exterior lights. The sound of a multi-beam sonar pulse sent downward from the hull of a ship somewhere above Challenger Deep takes more than 7 seconds to reach the trench floor and return. In those 7 seconds, the pulse travels more than 20 kilometers through water, descends to a place deeper than Mount Everest is tall, touches the pale sediment of the deepest ocean floor on Earth, and comes back carrying the shape of the bottom in the timing of its return. 7 seconds, there and back, and from those 7 seconds repeated thousands of times across a slow survey track, the map assembles itself, line by careful line, an image of a place built entirely from the interval between a sound going out and a sound coming home. Organic particles arrive at the floor of the trench, the way snow settles on a field in the dark, without announcement, without hurry, without any particular awareness that they have arrived. They have been falling for weeks. They began as living things in the bright water near the surface, caught the energy of sunlight, were eaten and passed through other bodies and broken into smaller pieces, and fell, all the while falling, through layer after layer of the ocean's cold and deepening dark. By the time they reach the sediment, 11 kilometers below the place where they began, they are very small and very changed. What they carry with them still is carbon. Carbon fixed from the water by the oldest kind of life, passed through gills and membranes, and the slow dissolution of countless small deaths, arriving now in the sediment of the deepest place on Earth, where a different kind of life waits to receive it. The sediment is pale and fine. To touch it would be to feel something between silt and powder, cold, slightly cohesive, faintly resistant, and ancient in a way that the skin would not know how to register. It holds the chemical record of everything that has fallen into it across millions of years. Silica skeletons of microscopic organisms press against clay particles the size of nothing familiar. Thin filaments of organic matter thread between them. The whole surface of the trench floor is like this, a continuous layer of slow accumulation, built grain by grain across deep time, resting under more than 1,000 times the pressure of the open air above. Into this sediment, carbon descends, and in the sediment, carbon is transformed. The bacteria and archaea that live in the upper layers of the trench's floor take up the incoming organic material, and begin to break it apart. They do this through chains of chemical reaction that are, in their broad logic, not unlike the processes that drive every other living thing on Earth. The breaking of bonds, the transfer of electrons, the extraction of usable energy from one compound, being converted into another. But the scale and the conditions and the result are entirely their own. At the floor of the trench, where the cold presses in from every direction and the pressure has no equivalent at the surface, these communities work in the dark without pause, cycling the carbon that arrives from above back into the dissolved chemistry of the deep ocean. What went up as sunlight comes down as particles and leaves again as dissolved gas and mineral ions, carried away in the slow movement of bottom water that drifts imperceptibly through the trench and out into the wider ocean basin beyond. The trench concentrates this process. Its steep walls funnel organic material downward into its floor. Its narrow shape means that the particles that drift horizontally through the water column tend to accumulate toward the center. Carbon that might in open ocean spread across a wide flat abyssal plain settles instead into the concentrated geometry of the trench's basin. And because of this, microbial carbon breakdown in the trench sediments runs faster than in the shallower sediments of the surrounding sea floor. More organic matter arrives per unit of area. More carbon turns over per unit of time. The trench, which is only a tiny fraction of the ocean's total area, handles a portion of the ocean's carbon that is larger than its size would suggest. Somewhere in the arithmetic of the planet's carbon accounting, the Mariana Trench and trenches like it appear as a term that cannot be ignored. This is not easily observed from above. Nothing about the surface of the ocean, passing in the light and wind above 11 kilometers of water, announces what is happening below. The trench is invisible from a boat. The chemistry proceeding in its sediments is invisible even to the instruments that have sampled them, except in aggregate, measured across many cores and many analyses conducted by researchers who have spent years learning to read the faint signals embedded in the cold, pale material brought up in tubes from the bottom. Science here works on long returns. A question asked in one decade receives a partial answer in the next. Each new sample opens onto more questions than it closes. The bacteria doing this chemical work are not surface organisms transplanted into the deep. They have been in the deep for long enough that the deep has made them into something the surface cannot sustain. A species of the genus Moritella, cultured in a laboratory under pressure that exceeds 700 times the pressure at sea level, grows and divides at a rate that normal marine bacteria, brought into the same vessel, never could. Its membranes are different. Where the membranes of surface organisms are built from fatty acids that remain flexible at ordinary temperatures and pressures, the membranes of these deep pressure bacteria are enriched with polyunsaturated fatty acids, longer, more kinked molecular chains that resist the tendency of compression to push membrane components too close together, stiffening them into rigidity. Under 700 bars, these membranes stay fluid enough to function. The proteins folded inside their cytoplasm hold their shapes under conditions that would denature the equivalent proteins in nearly any organism living above a few thousand meters of water. Everything about them has been calibrated by time and selection to fit a world of extreme compression, extreme cold, and total dark. When that pressure is slowly released, the calibration fails, the membranes stiffen, the proteins lose their configurations. The chemistry that sustains the cell slows and stops. A bacterium that thrives where nothing else can returns to something that can no longer metabolize in a world of ordinary water and open air. It is as precisely fitted to its world as any organism on Earth, and as profoundly unable to exist outside it. There is something in this that sits quietly at the edge of the known, not troubling but deeply still. The recognition that life in this place is not life that has descended and adapted, but life that has become the place as completely as the sediment itself. The genus Schwannella appears in the same sediments, in some of the same cores, working in the same cold. Its chemistry differs in emphasis, where Moritella tends toward the deep, truly piezophilic end of the pressure spectrum. Some Schwannella species bridge a wider range, found in shallower sediments as well, their optima less extreme, but their basic architecture still enriched and shaped by long residence in high-pressure environments. In a cubic centimeter of sediment from the upper layer of the trench floor, hundreds of millions of cells of these and other organisms are present, working, cycling, transforming in a space that could be held between two fingers. The density of this life is not visible and would not be felt, but it is there, and it has been there for far longer than there has been any human instrument capable of detecting it. Light does not reach this place. No photon from the sun has ever touched the floor of the trench. The darkness is absolute, in the sense that it has no variation, no rhythm of day and night, no brightening or dimming with the passage of seasons. The only changes in light come from the brief illumination of the few human instruments that have visited, and those lasted hours at most before the dark returned completely. For the organisms living in the sediment and just above it, light is simply not a variable. Their worlds are organized around pressure and temperature and chemistry and the slow arrival of organic material from above. In this, they are the same as they have always been. Sound, however, is another matter. In the autumn of the year 2014, a hydrophone was lowered into the Mariana Trench and left there. It hung suspended in the water column for more than a year, recording whatever acoustic signals arrived. Sound travels differently through the deep ocean than through any other medium most people encounter. The pressure and temperature structure of the water column creates a channel, a depth at which sound waves are refracted back toward the center rather than escaping upward or downward. And low-frequency sounds can travel through this channel for thousands of kilometers with very little loss of energy. The deep ocean is not silent. It has never been silent. What the hydrophone in the Mariana Trench recorded across those many months was a precise acoustic history of the world above. Earthquakes registered. Their low-frequency pressure waves traveled through thousands of kilometers of solid and liquid earth and arrived at the hydrophone as slow, deep rumbles, their signatures as specific as fingerprints to those who know how to read them. The tremors of distant faults, the slow groaning releases of stress accumulated over decades along subduction zones across the Pacific, all of it arrived in the trench, attenuated and transformed by its long travel, but present, legible, traceable to its source. The floor of the Mariana Trench sits at the intersection of more tectonic stress than almost any other place on Earth, and the record of that stress, accumulated and released over millions of years, is written into the shape of the trench itself and into the chemistry of its walls. Typhoons registered too. The instrument recorded the low, slow pressure signature of tropical storms moving across the ocean's surface, far above, their winds driving waves whose energy translated downward through the water column as infrasound, pressure oscillations below the threshold of human hearing that nevertheless traveled all 11 kilometers of water depth and arrived at the hydrophone as a real and measurable signal. A Category 4 typhoon passing directly over the trench produced a record that researchers could read later as a map of the storm, its intensity, its movement, its inner dynamics, translated into sound that had traveled down through the dark and been caught by a small instrument resting in the cold. Whales called from the surface waters, their long, slow vocalizations passing down through the water and arriving changed in tone and timing, but still recognizable as the voices of large animals moving somewhere high above. Ship engines produced their characteristic rhythmic signatures. Military sonar sent downward impulses from vessels conducting exercises somewhere in the vast Pacific arrived at the trench floor as precise, ordered signals from a human technology directed without knowing at one of the deepest points on Earth. All of this in the same water that holds the amphipods and the snailfish and the sea cucumbers and the pale accumulated sediment. The trench that appears from the outside to be the most isolated and sealed environment on the planet is acoustically open to everything. Sound crosses the boundary between the surface and the deep freely. The storms of the atmosphere arrive in the dark of the huddle zone. The calls of animals in the light reach the ears of instruments resting in the cold. There is no sealed world here. There is only depth, and depth does not stop sound. What sound carries down into the trench, chemistry carries too, and what chemistry carries is harder to hear and more troubling in its quiet. At the surface of the ocean, for many decades through the middle of the 20th century, a class of industrial compounds called polychlorinated biphenyls was manufactured in very large quantities and used in electrical equipment, in industrial oils, in paints and plastics, and 100 other applications. They were stable and persistent. That was their useful quality, and also the quality that made them, when their dangers became apparent, so difficult to remove from the world. They do not break down easily. They move through biological systems and accumulate in fat tissue, concentrating as they pass up through food webs from smaller organisms into larger ones. They were banned from production in the United States in 1979 and in many other countries around the same period. But the compounds manufactured before those bans remained in the environment, moving through the ocean in ways that no one had fully anticipated. In the tissues of amphipods collected from the floor of the Mariana Trench, polychlorinated biphenyl concentrations were found. In a study whose results arrived in the year 2017 to be 50 times higher than the concentrations found in crabs living in heavily polluted river systems in China. The number does not need to be made dramatic. It is already a fact. Compounds manufactured far from any ocean, decades before most of the people who would eventually read about this finding were born, had traveled through the ocean's water and food webs and settled into the bodies of animals living in one of the remotest places on the planet. The accumulation had proceeded through long organic chains, particle by particle, animal by animal, each body concentrating what the previous body contained, and the whole chain draining downward through the water column into the trench's concentrated geometry. Microplastics appeared alongside them. In the sediments of the trench floor and in the gut contents of hadal amphipods, fragments of plastic were found. Small, varied in source, varied in polymer type, uniformly present. The trench gathers what the ocean carries. What the surface world makes, the deep world receives, without asking for it and without the capacity to return it. This does not change the silence of the trench. The water is still cold. The pressure is still absolute. The amphipods are still there, converging on food falls in the dark, carrying in their tissues a chemical record of a century of human industry that they have no way to read. The bacteria are still breaking down organic carbon in the sediment. The sea cucumbers are still lifting themselves from the floor and moving slowly through the near-bottom water, with their bodies held horizontal in the dark. The snailfish are still drifting, translucent and soft, through the deepest water that fish have ever been found to inhabit. Life in the trench continues with the same patient persistence it has demonstrated across millions of years, carrying now a new set of compounds alongside the ancient chemistry of the deep. The question of what this means for the trench's ecosystems belongs to the open category, the long list of things about this place that remain genuinely unknown. That list is not short. The total number of species living in the Hadal zone of the Mariana Trench has not been counted. The counting is technically limited by the difficulty of sampling. Each trip to the bottom recovers a fraction of what is present, and the fraction changes depending on the type of sampler, the location of deployment, the depth at which collection is made. Species known from one trench have not been found in others. Whether Hadal populations in the Mariana are connected by larval dispersal or other mechanisms to populations in the Philippine Trench, the Kermadec Trench, or the other deep trenches scattered across the Pacific and elsewhere, remains a question with partial and provisional answers. The biology of isolation at this scale is not well mapped. The trench walls themselves are not stable. Occasionally, without warning that the organisms living below could detect or use, accumulated sediment on a wall gives way. What had been resting on a steep slope? Fine particles, organic material, biological communities attached to the substrate, releases and moves, a dense current of disturbed sediment flowing downward through the water and spreading across the trench floor. These events are called turbidity currents, and in the Mariana Trench, they have periodically reshaped the sediment surface in specific areas, burying whatever was living there under new material deposited quickly and from above. The record of these events is visible in sediment cores as distinct layers, sharp boundaries where one type of material ends and another begins, the signature of a moment when the slow accumulation of the trench floor was interrupted by a brief, significant event. What happens to the biological communities buried by these events is not known. How long recovery takes, whether the organisms involved have mechanisms for tolerating burial or for recolonizing a reshaped area, whether the chemistry of a freshly deposited turbidite layer differs from the surrounding sediment in ways that affect microbial metabolism. These are open questions. The trench has been reshaped many times. Its present surface is not its permanent surface. The biology sitting on top of it at any given moment is sitting on a surface that will, at some future and unscheduled time, be disrupted and remade. How life at the bottom of the world responds to this kind of change is something science has not yet seen clearly enough to describe. There is a quality in this kind of not knowing that is different from simple ignorance. The gap in understanding is not a failure of attention or effort. It is the natural limit of access, the difficulty of sampling a place 11 kilometers below the surface, in conditions that destroy most instruments and challenge even the most purpose-built vehicles, at a location in the middle of the Pacific that requires weeks of ship time to reach, and more weeks of careful preparation to sample even a small portion of the floor. Each answer recovered from the trench has required sustained work over years, and each answer has arrived attached to a new set of questions that the recovered answer made possible to ask. The knowledge accumulates slowly, in small increments, the way sediment accumulates on the trench floor, particle by particle, each one small, the whole slowly building into something with depth and structure. The cold holds. Down at the bottom of the water column, where the pressure converts the weight of 11 kilometers of ocean into something felt by every surface and every membrane, The temperature has not changed meaningfully since before any human civilization existed. The cold that sits at the floor of the Mariana Trench is not the cold of a winter night, or the cold of a refrigerator, or the cold of high altitude air. It is the cold of water that has not been warmed from above in tens of millions of years, that has been sealed from the sun's heat by its own depth, that has been stable and still while everything above it has changed beyond recognition. Ice ages have come and gone. Sea levels have risen and fallen by many tens of meters. Continents have moved perceptibly since the trench was last this cold, and they were already old when it reached this temperature. The cold at the bottom of the trench is geological in its stability. It is one of the most consistent conditions on the planet, and it has been consistent for longer than most conditions can claim. Into this cold, everything described above continues. Carbon arrives and transforms, sound descends and registers, chemistry accumulates, biology persists and varies and remains, in most of its particulars, unknown. The trench floor receives the world it sits below, quietly, without negotiation, in the dark. The pale sediment that covers the floor is softer than most seafloor material. It is made partly of clay particles that drifted down from the continents via river and wind, and partly of the siliceous remains of the microscopic organisms, radiolarians, diatoms, whose intricate glass-like structures survive the long descent even after the organisms themselves have died and been consumed. The calcium carbonate shells of other creatures dissolved before reaching the floor. The carbonate compensation depth, lying several kilometers above the trench. What arrives is therefore already filtered, the softer dissolved, the resistant preserved, and the sediment that builds on the trench floor is a record of what the deep ocean can and cannot hold. In the upper layers of this sediment, where the organic material is freshest and the bacterial communities are most active, the metabolic rate is highest. Going deeper into the sediment core, the chemistry changes. Older material has had more time to be processed. Electron acceptors have been consumed. The metabolic activity slows, and the communities change in character. The fastest metabolizing organisms, giving way to those that can extract energy from increasingly depleted substrates, living at rates so slow that a human observer measuring them would struggle to confirm they were happening at all. Life in the deepest sediment layers of the trench floor is living at what may be the minimum possible rate for living things, extracting the last available energy from material that has already been processed and reprocessed across thousands of years. Whether those organisms count as fully alive in the sense that the word usually carries, active, responsive, metabolizing at a meaningful rate, is a question that does not have a clean answer. They are not dormant in the way that a spore is dormant. They are metabolizing, slowly, continuously, without the pauses and revivals that dormancy implies. They are alive in the way that something can be alive at the very edge of the definition, where the boundary between a process and an object becomes difficult to place. The deep sediment holds them, cold and patient, doing what they have always done, at the slowest pace the chemistry will sustain. Above the sediment, the water column rises through 11 kilometers of dark and cold and pressure. There is no light visible in it. There is no temperature gradient perceptible at the bottom. The cold is uniform, held steady by the weight of water above and the distance from any heat source below. The sound of the world above passes through it, arrives at the floor, and is absorbed into the sediment and the water and the membranes of the organisms going about their chemistry in the dark. The acoustic record that the trench keeps is continuous and long. It began before there were ships or sonar pulses to record, and in that earlier record, there were only earthquakes and the calls of animals and the low-frequency signatures of storms passing overhead, each one fading and giving way to the next, the trench receiving all of it without distinguishing between the ancient and the recent. Well, a storm passes over the trench now. Its winds drive waves across the surface of the Pacific, somewhere high above. The waves generate infrasound that travels downward through the water column in the same way it has always traveled, indifferent to what is happening on the surface, indifferent to the world below. It arrives at the floor as a slow pressure variation, a faint oscillation in the cold that the hydrophone would detect if it were still there, that the organisms in the sediment are too small to feel, that the water accepts without being changed. The storm will pass, the waves will subside, the infrasound signature will fade and be replaced by the next signal traveling down from above. And below the passage of the storm, below the acoustic transit of the pressure wave through 11 kilometers of cold water, the trench floor will be what it has been. The sediment will continue to accumulate. Carbon will continue to arrive. The bacteria will continue their slow and patient chemistry, breaking the organic into the inorganic, returning to the dissolved ocean, the matter that the surface sent down. The amphipods will persist in the dark, tuned to chemical signals too faint to name, ready to converge when something worth converging on arrives. The snailfish will continue their slow passage through the deepest water fish have ever inhabited, their bodies yielding to a pressure that would collapse any structure built for the surface. The sea cucumbers will lift themselves from the sediment and drift above it with their bodies held out in the dark, gathering what drifts toward them in the near bottom water. The cold will hold. The turbidity currents will come again, in their own time, at walls whose stress has been accumulating since the last one broke and fell. The sediment will slide and settle and bury what it lands on. The floor will be remade in some portion of its area, and whatever was there will be covered, and what comes after will begin again on the new surface. This will happen without any witness, in the dark, under 1,000 times the pressure of the surface world. It has happened before. It will happen as long as the trench exists, which is to say, as long as the Pacific Plate continues its slow descent beneath the Mariana Plate, which is to say, for tens of millions of years still ahead. A duration in which every human structure now standing will have dissolved or been buried many times over, and the sediment on the trench floor will be correspondingly thicker and older and carrying a chemical record longer than any we can now imagine reading. The open questions will find answers, some of them in time. How many species live in the Hadal zone of this trench will become a number, provisional and subject to revision, the way all such counts are. Whether populations here are connected to those in other trenches or isolated from them by the vast abyssal distances between, will be worked out slowly through the comparison of genetic material recovered in future samples, each one requiring the same long ship transit and the same patient descent and the same careful work of preservation in conditions that tend to destroy what is not carefully protected. How the ecosystem recovers from a turbidity current may be observed, eventually, by instruments left in place long enough to catch one, and its aftermath, a patience measured in years of continuous deployment in a place where most instruments do not last. The planet will not wait for these answers, and neither will the trench. Both will continue in their own time, which is not measured in the units most familiar to those who ask the questions. The trench's time is measured in the slow convergence of plates, and the still slower accumulation of sediment, and the gradual settling of carbon through water, so deep it takes weeks to cross. Human curiosity, applied to this place, is very new.